During this blog, Gemma and I have discussed the components of the golf swing and how they can be used to maximize distance when driving. I'd like to now use this time to further explore once the ball's been hit. What happens in the trajectory? How does the ball travel now that it is considered a projectile? What I would like to touch on first is the ball launch velocity and how, hypothetically, that would be calculated. So, as you can see from the diagram, if the velocity of the ball is equal to that of the velocity of the club head times the coefficient of the restitution divided by 1 plus the sum of the ball mass divided by the mass of the club head, we can then add that equation into taking the loft of the club into that consideration. So, if that equation is the velocity of the ball, y, would be equal to the sum of cos times the loft squared multiplied by the sum of 90 minus the loft, so the complement times sin, then again multiplied by our original equation. So, to summarize, the key components that we need to know the velocity of the club head speed, the mass of the ball, the mass of the club head, the coefficient of restitution of the club head. We also then need to know the loft and the complement of the loft. Now, for obvious reasons and time constraints, I'm not going to actually punch in any extra values or unpack how those values would be determined, as some have been discussed already throughout the blog. Okay, so what we want to talk about now is what happens as far as the ball taking off. We've already mentioned the Magnus effect and the topspin. So we know that there's a pushing or a lift on the ball as a result of the Magnus effect. Okay, with really, really high swing speeds that result in quite high spin rates, the Magnus effect will increase on itself again. So in golfing lingo, players that can hit the ball incredibly hard off the tee are known as blowing up, in the way that the trajectory seems to almost climb and continue to climb vertically. Okay? In a perfect world, we would only consider top and bottom spin. However, in a practical sense, there's always going to be a proportion of open or closed club face. So with that, the ball is going to spin in the horizontal axis. So the path that the ball is going to follow is what we'd call, in a hypothetical situation, a parabolic path. Now, practically we know that's not true. We need to incorporate and calculate the Magnus effect into that. So we need to know the density of the air. Now that is reliant on our height above sea level. We also need to know the radius of the ball and also the angular velocity. So that's just one component, the Magnus effect. There's also going to be wind force and air drag. They all act on the ball in 3 dimensions of flight. So that's the X, the Y, and the Z plane. So we know that the X plane is the left and right direction or deviation of the ball in flight. We consider Y the height, and then we consider the Z axis to be the distance travelled ahead. Okay? So moving past that as well, we need to consider the drag force. So to know the drag force, which is the force acting against the ball as it's trying to move, we need to know the drag coefficient. Unfortunately, we're not going to get into that today because that's a little bit too deep. But once the ball reaches the top, its peak height, it starts to come back down. We know as golf balls are falling, as with any other object on Earth, it will be accelerating at -9 meters a second. Problem is, though, air resistance plays a role. So eventually the ball is going to reach a terminal velocity. So hypothetically, if a golf ball was to have a surface area of 14 centimeters square, a mass of 46 grams, and a radius of 2.1 centimeters, we can calculate that the terminal velocity of that ball would be 32 meters a second, or 115 kilometers an hour. That gives us some really interesting information, particularly when we start talking about driving off a cliff, as some golf holes do have, and the role that the terminal velocity would play in plateauing the speed. Finally, I'd also like to mention the wind force and wind speed. Again, we do need to understand the drag coefficient. However, this is again an incredibly complex formula. So what, in summary, I want to say is that understanding the way that the ball flies after impact is incredibly important in the practical sense when trying to maximize distance. We've spoken about the importance of torque, the importance of chemical, kinetic energy, muscle power, centripetal acceleration, the materials used, and so on. However, there are other phenomena after the fact that need to be considered so that we don't hypothetically try and push too far beyond what is realistic. I hope this has been informative and makes sense. Kim, thank you.